Welcome to The Explainer. Today we're getting into the core theory that really kicked off the whole deep learning revolution. We're going to look at how a major shift in thinking about training neural networks unlocked the insane power of depth.
So here's how we'll break it down. We're going to start with a huge problem, a real roadblock that was holding the field back. Then we'll get into the big breakthrough that smashed right through it. After that, we'll explore why that breakthrough was so powerful from a theoretical view. And finally, we'll see how it all pays off in the real world.
All right, let's set the stage a bit. If you rewind to before the mid-2000s, the idea of a truly deep neural network, one with tons of layers, was pretty much just a dream. I mean, researchers had this gut feeling that more layers should mean more power, but every time they tried it in practice, it just fell flat.
So the big question, the one that had everyone scratching their heads, was this: why did adding more layers often make the network perform worse? It made no sense. They'd hit this wall where performance would just plateau, and then, get this, it would actually start to get worse, even on the data it was trained on. What in the world was going on?
Well, the culprit, it turns out, was the learning signal itself, the gradient. You know how during training that error signal gets passed backwards from the end of the network all the way to the beginning? Well, with a lot of layers, that signal would either just vanish into nothing, or it would explode into some ridiculously huge number. Either way, the layers at the very beginning of the network were basically getting no useful information. They just weren't learning. It was like trying to whisper a message down a really, really long line of people. By the end, the message is either gone or totally garbled.
Okay, so that was the problem. Now for the solution. Because in the mid-2000s, a really brilliant insight came along that just changed everything. It was this super clever workaround for that whole gradient mess. And it's what kicked off what we now call the third wave of AI research. Basically, the dawn of the deep learning era. And look, this wasn't just some tiny incremental step. To put it in perspective, the first wave back in the 40s and 60s, that gave us the basic idea of a neuron. Then the second wave in the 80s gave us backpropagation, which was awesome. But it really only worked well for networks with like 1 or 2 hidden layers. This third wave, starting around 2006, this is when we finally cracked the code and could train these really, truly deep models.
So what was this big idea? It was actually pretty radical at the time. The idea was to just stop trying to train the whole network, all the layers, all at once from a random starting point. Instead, the new approach was to build the network piece by piece, one layer at a time. They called it a greedy approach. And the craziest part? At first, you didn't even use the labeled data. Okay, so here's the play-by-play. You start with just the first layer. You feed it your raw data, and you train it to be what's called an autoencoder. Basically, its only job is to learn how to squeeze the data down into a compact summary and then recreate the original from that summary. That forces it to learn the most important features. Then, and this is the key, you freeze that layer, lock it in. You take its output, its summary of the data, and use that as the input for the next layer. And you just repeat that process, layer by layer, with each one learning more and more abstract features based on the one before it. Only after you've built this whole stack do you add your final output layer and fine-tune the entire thing with your labeled data. It's like giving the network a really, really good head start. So, great, we can now train these deep models, but that leads to the next big question. Why? Why go to all this trouble? Is a deep 10-layer network really any better than just making a single layer that's super, super wide? Well, the theory came back with a resounding absolutely yes.
And it's not just a little bit better. They work in a fundamentally different way. Think of a shallow network like a single tool, maybe a knife. It can divide the world into regions, this side and that side. To solve a complex problem, you need a ton of these simple cuts. A deep network, on the other hand, is like a whole assembly line. Each layer performs an operation and then passes its work to the next layer, which performs another operation. It builds complexity step by step. And here's the absolute kicker. The advantage you get from depth isn't just linear, like adding a little bit more power with each layer. It's exponential. That's huge. It means that for some complex functions, a shallow network would need an exponentially larger number of neurons to do the same job as a deep one. We're talking about an insane increase in efficiency just by stacking layers.
Here's another way to think about it that I really like. A deep network is basically a multi-step computer program. Each layer is like one line of code, or one set of instructions, that runs. The output of that layer is like the new state of the computer's memory. So, the deeper your network, the more steps your program can have, and the more complex a computation it can perform.
And this is how that exponential power actually works, mechanically. Imagine each neuron folds the data space, kind of like folding a piece of paper. With every new layer you add, you're folding the already folded paper again. And what happens? The number of little regions you create grows exponentially. This is what allows deep networks to carve out these incredibly complex, intricate patterns with surprising efficiency.
All right, so let's recap. We've figured out how to train deep models, and we have a solid theory for why they're so incredibly powerful. So what's the payoff? Well, this is where it gets really practical. We can now take these amazing learned representations and use them to solve completely different problems.
And honestly, this is where the magic happens. It's this idea that you don't have to start from zero every single time you have a new problem. Instead, you can take a massive network that's already been trained on a huge data set, and you can leverage all that knowledge, that whole hierarchy of features it learned, for your new, much smaller task. And this amazing trick is called transfer learning. And the workflow is actually super straightforward. You grab one of these giant pre-trained models, you snip off the very last layer, the one that was specific to its original task. Then you freeze all the other layers so they don't change. All that's left to do is stick a new small classifier on the end and train only that new part on your specific data. It's incredibly efficient because you're standing on the shoulders of giants, building on this rich foundation that's already been learned.
You see this being a total game changer in natural language processing. Think about it. The old way to represent words was something called a one-hot vector. The huge problem there is that the representation for cat is mathematically just as far away from kitten as it is from automobile, which is nuts, right? But with pre-trained word embeddings, words with similar meanings are naturally clustered together in space. This kind of representation is just worlds more useful. It gives any new language task a massive, massive head start.
So when you boil it all down, what's the real goal of all this pre-training? It's to find a representation that makes your new problem easy. The network's job is to take this tangled, messy ball of data and warp and stretch the space it lives in until, poof, the different classes are just cleanly separated. So clean, in fact, that a super simple classifier can just draw a straight line between them and call it a day.
Okay, so let's bring it all home. This whole journey, from being stuck with shallow networks to building these incredibly powerful and flexible models, it really comes down to three key ideas, each one building on the last. First, the breakthrough. That whole greedy layer-wise pre-training thing gave us a way to finally train deep networks. Second, the theory. We realized that depth wasn't just a nice-to-have. It gives an exponential advantage in what a network can represent. And third, the payoff, transfer learning. The realization that these powerful representations can be reused to solve new problems with way, way less data. That's what made deep learning so practical.
And that leaves us with one last big, kind of mind-bending thought. As we get better and better at learning these powerful representations that can jump from one task to another, from images to text to sound, you have to wonder, are we getting closer to finding some kind of universal language of data? A fundamental structure that underlies everything?